So I thought I'd do a recording of this problem from I think it's section 2.04. It's about complex zeros and the fundamental theorem of algebra and putting it all together. I thought that's why this was a good problem. One of my students, one of you asked about a problem like this. So this problem I'm choosing to do out of the online textbook asked me to find all the zeros and write a linear factorization of all those zeros. And so that's the function that one of the ones you were supposed to do that they recommended you do. So I thought I'd walk you through it because it's nice about it. It puts it all together. All the pieces kind of fall together nicely for this. So before I start, I thought I'd graph it just to see where we're headed. And what I'm seeing is I'm seeing a fourth degree equation like I knew I would. And I'm seeing two zeros, and it looks like they're rational. It looks like negative 2 1/3 or negative 7/3 is a zero, and it's a negative 0, and then positive 1 1/2 or 3/2 is also a 0. So those are both rational solutions, rational roots. And then, but I've only seen two, and the fundamental theorem of algebra tells us because this is a fourth degree equation, there's supposed to be 4. So there's going to be two complex roots here. Just make sure I say this again. There's going to be a negative rational root, a positive rational root, only one of each, then the two complex roots. So that's where we know is going to happen. Now let's go find them. Okay, so Descartes' Rule of Signs tells us how many and what kind of roots there could be. So for this one here, I'm counting, let's see, I'm counting one change because it's going from a positive 6 to a negative 7. So there's a change in the sign. Nothing there. There's another change in sign. So that could be 2, and then there's a third one. So this is telling me that there could be three real roots. I don't know if they're rational or not. And if there's three real roots, that means there can be no complex roots because complex roots always occur with those conjugate pairs. So if there's three real positive roots, it'd have to be one negative root. Now, and then, or the other possibilities, remember how these decrease by 1. So that tells me there could be one real root and there could be two complex roots. And if you think back when I looked at the graph, we did see there was one real root and two complex roots. So this is probably where we're going to head. But now let's examine the negative roots. Descartes' rule of signs for the negative roots. So I substituted in f of negative x, and that, of course, raising a negative value for the fourth degree doesn't change the sign. Raised into the third degree, remember how it was a negative 7? Well, now it's a positive 7. Squaring a negative number doesn't change the sign. This was just x to the first, so that positive changed to a negative, and of course the constant doesn't change. So now what I'm seeing is one sign change right there. That tells me there could be one, there will be one negative real root. And there won't be any complex based on this one. So looks like the solution we're going to go for is the one positive real root, one negative real root, and then there's going to be two complex roots. And of course, we knew that if we go think about our graph. So then what are the possible rational roots? So I listed all the factors of 105 on top, here, plus or minus. I listed all the factors of 6 on the bottom. And then I can decide what's a good choice, what's a good one to go with. Well, let's see. I mean, I could try 5 or 7 or 15, negative 15. And the reason I want to go with the negative is because I know there's definitely one negative real root. So I'm going to pick a negative number, and I could try plus or minus 1. I could try negative 1, but I've decided, why don't I try x equals negative 3? and see what happens with that. So I decided to use some synthetic division on the original polynomial. I'm testing -3, and I dropped it in, and you can follow along. I'm hoping you remember how to do synthetic division. Well, I'm talking about it right now because you've had some practice. And then what I'm seeing is I'm seeing alternating sign changes. And if you think back to that part, that lesson about lower bounds and upper bounds, if the number you're testing to see if it's a lower bound is negative, and the last line of your synthetic division alternates positive, negative, that tells me I know that x is -3. I don't even have to bother with -15 and all those other possibilities. So I know -3 is too low, so it won't be -3. So I could try -1, or why not -7/3? Because that was one of the possible roots if you go back and look at all those listings. And of course we know that's the answer because I looked at the graph. But that would be one to try, and then I just ran the synthetic division through this, and maybe I'll walk you through this in case somebody's a little shaky. So I brought down the 6. I said, so in what I did in my head, I said 7/3 times 6/1. Well, the 6 cancels the 3. That leaves me 2. -2 times -7 times 2 is -14. I combine like terms. I got -21. Think about 7 canceling the, so maybe I better write that. -7/3 times -21/1. The 3 cancels in the 7, and I get, and 3 canceling the -21, I get -7. -7 times -7 is +49. Combine those, you get 48. 48 divided by 3 is 16. 16 times -7 is -112. Combine those, you get -45. -45 times, well, 45, 3 goes into 45 15 times. Negative times a negative is a positive. 15 times 7 is 105. Cancels out, you get a 0. So -7/3 is a 0. So then I got to take a look and test one of those pies. So there's one negative solution. I knew there was going to be a negative solution. So now I got to test and see if there's a positive solution. So I looked back at my list of possible rational roots, and I saw I could have done +3, +5, +7, 7/2, 5/1, 3/2. I chose to use x equals 3. Nice small number. So then when I ran the synthetic division for x equals +3, I'm noticing these are all positive. And that was that upper bound test. If you are testing a positive number to see if it's a 0, and the last line of the synthetic division is all positive, then you know this number is an upper bound. There won't be a number any bigger than that that's a 0. So I won't even try that. Anything bigger than 3. So then I got thinking about the possible roots, and I said, well, 3/2 would work. That was one of the possible rational roots, and I'm just going to run it right through my last line of that synthetic division that I did when I found out that -7/3 was a 0, because I'm trying to factor this thing down, right? So brought the 6 down. 6 times 3/2. Remember, 2 goes into 6 3 times. 3 times 3 is 9. Add those together, you get -12. 2 goes into -12 6 times. -6 times 3 is -18. Combine those, you get 30. 2 goes into 30 15 times. 15 times 3 is 45. And then -45 plus 45 is a 0. So I know that -7/3 is a 0. I know that 3/2 is a 0, and it could be that there's 2 more positive real roots. So let's see where we're going from here. So the other aspect of this problem was to write the linearization. So here's a 0. If I want to write this as a factor, I'm going to multiply by 3. That's where I got the 3x from. And then add 7 to set it equal to 0. So there's a factor. There's a linear factor. Same thing for the 3/2. Multiply by 2. Got 2x. Subtract 3. I know that's where it's equal to 0. So those are two linear factors. And then I've got this thing here. And how do I deal with that? So what I did is I actually went through and redid the problem where I did long division, polynomial long division on with that factor, the x equals -7/3 factor, and I ran through the polynomial long division. I won't walk you through it. You can stop this video and take a look at my work if you want. If you really want to, I can upload the sheet. I think I can. I don't think I threw it out. And then this was the quotient. And notice there was a 0 remainder, so I know that this is a factor of that big thing. And then, so I wrote, what I did is I wrote, there's my first factor and the remainder, the quotient. And then I ran the x equals, remember x equals 1.5 or x equals 3/2. There's the factor. I ran that through, and again, it worked out to be 0. I think you can see that at the bottom of the screen, and then that's the quotient. So looking at the results for my polynomial division, there's the first factor, there's the second factor, and there's the last quotient. So now what I was going to talk about, how come this was my last line of the synthetic division when I ran through 3/2. Why aren't these numbers matching up? Why don't I have a 6x squared here, a minus 12x here, and a 30 here? Well, when you do the synthetic division with a rational solution, it introduces these extra factors, and I honestly don't have a good reason why. I haven't found a reason why. That's the way it is. So when I'm doing synthetic division and I know I'm dividing by a rational number or a fraction, I know it acts as a multiplier to get these answers. So 2 times 3 is 6. So if I factored a 6 out of each of these, I knew that's what the result was. And notice there wasn't a 6 for a GCF in the original problem. So I know that I introduced that 6 by doing this synthetic division twice with those fractional exponents. You have to do synthetic division. No, you can do long division if you like it. Go ahead. Certainly helps you prevent from making this kind of mistake. Okay, well, it's not a mistake, but neglecting to account for it. So here are the factors so far. This is not a linear factor, so I should try to do something about that. Try to factor it. Maybe I'm going to use quadratic formula, maybe completing the square. So it didn't factor. I tried to factor it. So I know the factors of 5 are 1 and 5, and there's no way I can get those to combine to -2. So I know this is going to be an irrational or complex answer. Actually, we know it's going to be complex if you think about that graph. So here's the quadratic formula. Remember, it's -b plus or minus the b squared minus 4 times the 1 times the 5. And 4 times 1 times 5 is 20, -20. 4 minus 20 is -16. The square root of -16 is 4i, so plus or minus 4i. And then I can divide both of these by 2, or really what I'm doing is I'm factoring out a 2. Right? If I factor out a 2, that's going to leave me 2 times that over 2. That 2 cancels, and that's where I got the 1 plus or minus 2i. And then, of course, that x equals that. X equals that. So to set it equal to 0, I subtracted this to the other side, put a negative there. I subtracted this one to the other side, and then I distributed the negative through. Okay. And then here's all my factors. I've got my real number, one real number factor. That was my negative root. Here's my positive. Here's my factor from a positive real solution. That was my positive root. And here are my 2 complex roots. So I was able to put together the the Descartes Rule of Signs test. I was able to put in the bounds test, the upper and lower bounds test, and then I was able to find the solutions. And that's how this problem works. It was a lot to it, but it's doable.